4 же рядом, докладчик тоже почти рядом.
В общем, я бегу в туалет, а ты можешь управлять как хочешь. Ладно?
Не.
Онлайн.
Дима, слышно меня? Дима, слышно меня? Привет, Дима. Можно я тебе пришлю по WhatsApp ссылку на YouTube, а ты тут в чате оставишь, чтобы люди могли посмотреть?
Содействие объяснения, пожалуйста, дайте аудио. Кажется, не надо.
Значит, как договаривались по-английски.
Да, по-английски.
Так, на этой доске.
Да, на этой доске. Сейчас я маркеры принесу еще. Да, кстати, я снег много иностранцев.
Много?
Да.
А из Европы есть кто-нибудь?
Правильно. И всегда есть. Да, потому что он на доске будет писать.
Я могу, например, его здесь транслировать. Могу транслировать YouTube здесь.
Кстати, да. Это можно, да? Да, будет транслировать свой экран, да?
Да, только я хочу убрать все лишнее, чтобы... Ну, давайте я попробую вот так. Так же видно?
Да, видно.
Не очень здорово.
Мне кажется, пока нормально. Только может быть будет задержка с трансляцией. Но посмотрим.
Надо убрать монитор немножко.
Да.
А где вообще расположена видеокамера?
Вот здесь? Но я сейчас пришлю ей вторую камеру.
Еще нет.
Одну секунду, я там.
Маркеров у Маркеры вы не брали?
Сатирис сказал, что он должен пойти взять какие-то еще, наверное, я не знаю.
Да.
Да, Дима, в принципе, можешь представить докладчика. Да, да.
Yes, Pavlov will talk about extended KP hierarchy and its two-dimensional reduction. Today we have a translation of YouTube, young chat.
Просто свои.
Сделай, пожалуйста, погромче. Please start.
Yeah, thank you very much. Satiris, just first question. Can I use any of these markers?
Yes, please.
Well,
I think they don't write very well.
Okay. So, I'm happy to be here because I was already twice in Yaroslav and just this is my first occasion to visit this university, so I'm very interested. Indeed, nice weather, nice country view. So, okay, I can start. So, I will speak about KP hierarchy and its reductions, two-dimensional reductions. So, of course, I will try to explain everything, but please do be not extremely confused because I try to avoid most formulas due to
Что дай мне?
Ну, дай послушаем вопрос.
So I will try to avoid most of writing formulas because I will of course speak about hidden difficulties, computational difficulties. So I will write first only necessary formulas, and in each case I will say if you would like to derive corresponding integrable systems, you need to check some compatibility conditions. So of course I will avoid this computation. So I will follow standard technology. I recently had talked with some of my friends who are experts in the direction of commutative differential operators. Of course, I'm speaking for simplicity only about scalar case, and even in scalar case, corresponding computations are extremely complicated. So that I promised you, I will speak about difficulties about these computations, but I just try to explain in this simplest case. I'm speaking about KP hierarchy, how corresponding computations could be complicated. So possibly, that I would like to emphasize, this construction comes from Gelfand decay, or maybe this is some Japanese school, Japan. So both directions have some regular tools which allow me to construct first sector, integrable sector in KP hierarchy. I'm going to explain what I'm talking about. So, let us introduce special operators.
There's no sound.
Звук идет оттуда или оттуда?
Микрофон здесь.
Тогда я должен мьют. Или
Да,
нет?
да, ты должен мьют.
Хорошо. Тогда у меня нет, они говорят нет.
Спросил, открой микрофон, спросил Дима.
Дима,
Звук есть, Дима?
вот
На
сейчас
YouTube.
есть, потому что у меня микрофон.
Нет, не слышно ты меня.
Может, кто-то не понимает, что надо в YouTube звук брать?
Ну, скажи Диме. На YouTube звук есть.
Дима,
может написать в коммент или как-то, что...
Chat.
В чат, да.
Chat for everybody.
Да.
Да, согласен. Да.
Надо сказать всем, что звук в YouTube.
Да,
А,
скажи
нет,
Диме,
нет.
потому что Дима транслирует.
Okay, let me repeat the translation. The colleagues, it's better to look the report on the YouTube. The YouTube link is given on the chat of this conference.
Да, все есть.
Let us try again.
Yeah. From the beginning.
No, I think he means with the sound.
Mhm.
So Dima is trying to translate to do this streaming on Zoom, but it's better if people just watch on YouTube.
Victor, have you found the YouTube link?
Okay.
Okay, we can.
Okay, Maxim, please continue.
Uh-huh.
Yeah.
So, we introduced special so-called pseudo-differential operator. Pseudo-differential operator. So, dx plus a naught dx minus 1, a1 dx minus 2, a2 dx minus 3, etc. Infinitely many terms where functions a k depends on x and t. T means T1, T2, T3, T4, etc., where x I identify as just T1. This is such a procedure. So now I have dependence only on x. So dx standard derivative, and this is inverted operation. So this is so-called pseudo-differential operator. Just few words about origin of this operator. Few words I will write and I will erase. I take the red one. So let us consider KdV case. KdV. We have Lax representation where the first equation can be written in the form lambda square minus u psi. This first part of Lax representation for KdV. Then we would like to say, I would like to rewrite this equation in a form lambda psi is some operator L acting on psi. So I'm looking for such operator L such that it will be just reformulation of this linear problem. So what I'm talking about, you need lambda psi in this form, substitute here, and just try to find what is it A. Answer is following this one, where A0, A1, A2, etc. will be differential polynomials with respect to function u and its first, second, and higher order derivatives with respect to x only. It will be just a result of corresponding computation. So again, we had Lax representation for KdV. This is first equation of 2 for KdV. We say, I'm looking for special operator L such that
Pseudo-differential of the same type.
better to say, here should be a proof that if you are looking for L, answer is given by this form.
But is the proof that the only
I
pseudo-differential...
think so. I have no proof.
But at least there is at least one pseudo-differential operator satisfying that
Yes,
equality.
yes, yes. So I guess that once such observation was made, so let me repeat again, this is important. Here I am speaking about 3D, 3 dimensions. Now I am speaking about 2D, 2 dimensions. I am speaking about history, about origin of this Lax Satos-Field differential operator. Possibly, explanation is following. If we would like to rewrite linear problem of second order with such quadratic dependence on spectral parameter lambda in this form where we have in fact eigenvalue problem for some unknown L operator, answer is that L satisfies these answers where every coefficient depends on u, ux, uxx, etc. So they are differential polynomials. But now from 2D, I come back to 3D. So it was naive hint, and then I use this hint to extend this hint to 3D picture.
Why is it 3D?
No, I said I am going to speak about 3D. This is my intention. I am going. Okay. It was just explanation, possibly, how this operator appears in a integrable system theory. Okay. So, three. Let's introduce infinitely many pure differential operators, which I will determine by following answers. 1 over k, L in degree k, cross. Cross means that I take this L operator with infinitely many functions, infinitely many. I just compute corresponding natural, k is a natural number, so k is 2, 3, 4, etc. natural number. I compute corresponding degree, and then I take non-negative part. Because if I started from pseudo-differential operator, this operator has only this non-negative part dx, all the rest are just terms from negative side. So when I compute multiplicative application of this operator, if I take non-negative part, means I compute by this procedure corresponding pure differential operator. Examples: L2 is half dx squared plus u, where u is a naught. L3 is 1 over 3 dx 3 plus u dx plus v, where v is identically a1. And if I will continue these computations, I should be able to compute L4, L5, etc. Here I will write differential polynomials, but important to emphasize that the fact that u is a0 and v is a1, this is just coincidence. Because for other cases, all factors for corresponding every degree will be differential polynomials. This is not just a function. Differential polynomials of a0, a1, etc. Here, in these two steps, this is just coincidence. For higher steps, you will have definitely
L4, you are not going to write down L4. Just, okay.
I'm not going.
Okay.
Moreover, I stop here because next every step is much more complicated.
Okay.
Everything grows rapidly. So this question of computer algebra, necessary to write appropriate procedure to find corresponding elements. And in fact, in some sense, for me, it's very interesting question. We have coefficients a0, a1, a2, etc. What we can say about corresponding differential polynomials, which will be factors of every degree dx or other LK differential polynomials. So we have differential polynomials, differential polynomial operators, LK, and every coefficient of every degree dx, every factor, is already differential polynomial with respect to a0, a1. So what are these polynomials? I don't know. So it's an interesting question for me. I saw some papers where people started to write corresponding expressions. They just grow, and it's difficult to say anything about these polynomials, but it's an interesting question. Okay, so this way how to write operators. Yeah, and now you see everywhere we have derivative with respect to x only. But I said we have x and infinitely many other time variables t here. So how to incorporate higher time variables t if I would like to construct integral hierarchy that I'm talking about kp hierarchy, how to construct. Idea is very simple. So I write psi tk common function psi, scalar function psi. No any vectors, no matrices, only scalar function psi. I differentiate psi with respect to t with up index k. So this is not degree, this is up index. And here I write lk psi. Lk psi. What is the lk? You already know. So, examples. I have psi t is half psi xx plus u psi. Please see here.
T2 you mean?
No, I'm going to write. Psi y is 1/3 psi xx.
Максим,
Yeah.
there are recursive formulas for all the coefficients of
Okay. Okay. So u psi x plus v psi, where I introduce for simplicity notation that t is identically t2 and y is identically t3. So this is simplest such an example. Simplest, because in all other cases I will write more and more complicated expressions. So, two first linear equations, I'm speaking about Lax pair. So I have ak functions of x and t, and I have function psi, which is a function of x, t, and parameter lambda. So, ak do not depend on lambda. Function psi depends on this parameter lambda. And of course you can ask me, how to understand this? That parameter lambda is hidden in both equations. How to understand?
So the psi depends also on y, right?
No. X, t, t2, t3, t4, t, y,
Okay, psi depends on all, okay. Yeah.
on all. Yeah. If you wish, t vector. Yeah.
Oh, okay,
Infinitely
yeah,
many.
yeah, that's nice. Because you have t also is equal to t2 in the last line, right? So it's nice to have the vector. It's
T, y, lambda. Yeah. In my case.
okay.
In my case. So, where is a parameter lambda in this 3D construction? Because here you see Lax pair.
Is it similar to, is it in the derivative with respect to y? Well, in the, when you get the Lax pair for kp, you don't have special parameter, yeah? So you just technically replace it by derivative with respect to y, no?
No. This is first equation. This is second equation. And where is the equation for lambda? equation for lambda is here. Lambda psi is L psi.
Ah,
So this means I again refer to Gelfand-Dickey and Japanese school in integrable systems that this extra third equation is in some sense very artificial because this is in some sense useless. I have infinitely many terms. This is U, this is V.
yeah.
All others do not depend on U and V. In any way, do not depend. So this is just extra auxiliary equation, which in fact is useless. If I'm speaking about Kp, I use usually only these two equations. This is not necessary to use. Just explanation that parameter lambda is every time inside of this construction because this is common hierarchy. I take L operator, I take this eigenvalue problem for this pseudo-differential operator, I organize L2, L3 according to this rule from the same pseudo-differential operator. So this is common picture. I have only one Lax Sato pseudo-differential operator. I use this operator to construct infinitely many pure differential polynomial operators. And in this way, I write two equations which determine Lax pair for Kp. But this is third one, so no any contradiction. I can write, I can forget, just I write it because I would like to emphasize that lambda is every time here, but this is hidden. Why it's hidden? Because it's hidden in this equation, which is in fact auxiliary part of my construction. Usually we never refer on this case. Usually.
It's very nice because the right hand side, it's not clear how to define the right hand side of this equation.
Yeah. Okay, so instead of psi t2, psi t3, I could take any time variables, so I can say that once I use this formula, how to determine dependence of function psi and coefficients A0, A1, A2, etc. in this Kp hierarchy, how to determine its compatibility condition. Of course, as usual, we need to take psi tk, tm, and just for all indices, I need to check compatibility conditions. This means that when I will open parentheses, substituting corresponding expressions, I shall be able to write corresponding 3D equations. I have x by definition, because every operator contains dx derivative, and I have corresponding tk, tm. So I have x, tk, tm, this triple for every 3D system inside of Kp hierarchy. So this way how Kp hierarchy is determined, as you remember at abstract of my talk. So I said first part of my talk is devoted to so-called pure differential sector. This is pure differential sector. Everywhere I have special rule how to determine pure differential operators. I determine them, I check compatibility conditions according to this procedure, and finally I should be able to write corresponding 3D system for coefficient A0, A1, A2, etc. This is a way how to do this job. So this is 3D picture. Okay? If you agree with me, I would like to erase
Yes, please.
most.
So it is 3D because we have x, t, and y.
Yeah.
In the general case, x, tk, tm.
Yeah, for any indices. For any indices. 1 million, 1 milliard. Why not?
So it's always 3D for every k and n.
Yes. Because this system is a member of Kp hierarchy, and for every 3 indices, such a system can be considered as independent. As independent. Okay. Now I am going to speak about 2D. 2D. I had talked about 3D, now I'm going to tell you about 2D. So you see, what I said previously. I said following. We have Lax status U, the differential operator, with infinitely many functions ak. Then we now rule how to construct pure differential operators. Then we have a way verifying corresponding compatibility conditions, how to derive 3D systems. But now I would like to construct 2D systems. I would like to know what to do. First idea is following. Again, we have Lk, 1 over k, L in degree k cross, k is 2, 3, 4, etc. Now I have function psi which depends on x, t, and parameter lambda, you remember, such that psi tk is L k psi. So, example, I have psi t2, or maybe I again will erase psi t is L2 psi, psi y is L3 psi. So again, I wrote here example. Example means that instead of L2, L3, I can write L5, L7, doesn't matter. So any natural numbers. And I can call them T, Y, okay. So I have this pair. This is 3D. So what means this is? This is Lax pair. If you check compatibility condition psi ty equal psi t2, this means that for coefficients, you remember u and v, or a not a1, you should be able to derive some system of equations which is known as Kp in this particular case. Next step, 2D. I would like to construct solutions. What to do? First, let us add third equation. For instance, psi z is L4 psi. Again, example. Instead of L4, I can write L5, L7, L1 million, doesn't matter. I take any operator because you remember this rule. Anytime I take. And so this is T4. T2, T3, T4. So I have this pair of equations and I add the third equation. So here is an important feature. Some people know such a concept. Darboux method. What it means? You have some system of nonlinear equations. You would like to construct some particular solution. So you say, I would like to add some extra constraint which in intersection with given nonlinear system give us some subclass of solutions. In theory of integrable systems, instead of this idea, we speak about Lax pairs. We have Lax pair, we added third equation, and I say, I would like to use in some way, I am going to explain what is it. I would like to use in some way this extra third equation to construct particular solutions of this, in this particular case, Kp determined by corresponding Lax pair. So how to use this third equation? Idea is following. This is so-called stationary ansatz. Instead of function psi of x, t, y, z, now I do not write lambda. I do not write. So you remember, previously I had L psi is lambda psi. So I'm no longer use it. A little bit later we will come back here. Now I say, let us consider such a reduction, stationary answers, where I write x, t, y, x, t, y, multiply on exponent lambda, you remember lambda, lambda z. Let me emphasize again. Now I forgot about this question. Not forever. For a few minutes, I forgot. And now I say, let us substitute these answers. So what is the meaning of these answers? What is the meaning of these answers if I wrote here stationary? This means that I split dependence on all independent variables x, t, y, z according to following rule. Function phi depends on x, t, y, but evolution with respect to time variable z, in this particular case, this is t4, is such that lambda is a constant, some parameter, and this is very useful from the point of view. You see, if these answers for psi I substitute here in this equation, I come to phi t is L2 phi. Nothing changed. So this substitution is such that this factor disappears from this first equation, because this is constant from that point of view. What about next one? I will write phi y is L3 phi. Again, this factor disappears from this picture. But when I use this equation, this function phi no longer depends on z. So when I compute derivative with respect to z, I have just factor lambda. This means that third equation transforms to lambda phi is L4 phi. This is my new Lux triple. So I got Lux triple. And last question, that of course you can ask me. What is the relationship between this equation and this equation? The relation is following. This is differential operator of fourth order, you remember, due to construction of fourth order. So this means that if I scale lambda to 1/4 lambda 4, I just scale parameter lambda. Instead of lambda, I write 1/4 lambda in degree 4. Then I take quadratic root. I come here. So this is just consequence, where all coefficients, this is important, a dx plus a naught, dx minus 1, a1, dx minus 2, etc. So where all coefficients will be differential polynomials. So they are no longer as it was in 3D picture, in 3D. They were independent. Now in this 2D picture, the differential polynomials of first elements in this picture, a0, a1, a2. Okay. So I have still one equation. I have second equation. This pair of equations is nothing but Lux representation for Kp, precisely like here. But this third equation I used to cut Lux representation for Kp on two parts. This means that I use this third equation, introducing spectral parameter in explicit way, instead of this picture, which is just pure artificial. Here is everything is determined. So once I check compatibility condition of this equation and this equation, this equation and this equation, I come to two commuting multi-component 2D systems. This is the point. I had 3D KP. Once I determine this extra equation, this means that I split KP, 3D KP, to two 2D commuting flows.
And what are the two independent variables now?
So 3D, I changed to 2 on 2D systems. So one system has x, y, second x, t. X is a common time variable because it inside everywhere of this operator. T2 and T3 you can meet only in left hand side. It's enough to keep here T and here keep to y. So once you do this computation, again, Sergey, if you take this equation and this equation, here no y, y is hidden. If you take this equation and this equation, T is hidden everywhere. So when you check compatibility of these two equations, you have evolution only with respect to T. Once you check compatibility of these two equations, you have evolution with respect to Y.
So then in the first equation, y is a constant,
Precisely.
and in the second, the t,
So-called
t is a constant.
group parameter, hidden group parameter in this construction.
Okay,
Yeah.
okay, very nice.
Yeah. Okay, it was construction in some sense. I will explain everything. In some sense, universal. What means universal? I said, let's take T2, T3, and T4. But you can take, I would like to take any other integers. I can take 1 million, 1 billion, 1 quintillion. Okay, it works every time. And of course, here T2, T3, T4. But you can change any indices. For instance, here could be T5, T7, T2. Why not? This is just infinitely many ways. For instance, if you keep T and Y as T2 and T3, changing here index of corresponding pure differential operator, you will select infinitely many ways how cut 3D KP to variety of 2D two computing systems. Just number of independent field variables will increase once you will increase degree of this differential operator. In simplest case, you will have 3 equations and 4, 5, etc. So this is growing picture, and unfortunately it takes time. And just very important observation that I would like to mention now, because this is also very important for me. Just again, this is observation, and nevertheless I believe that this is interesting observation. Observation is following. Let's take psi T2, L2 psi, psi T3, L3 psi. Let's take psi T2, L2 psi, psi T4, L4 psi. I don't remember how many different choices, but at least maybe 4 or 5 options only. So here index k run from 2 up to infinity. Now I'm speaking about possible combinations 2 and 3, 2 and 4, maybe also 2 and 5, 3 and 4, 3 and 5. That's all. If you check compatibility conditions of such linear systems, you come to some members of KP hierarchy which have Lagrangian representation.
Only them.
Only them. I mean local Lagrangian representation. Local. What is important for me? You see, this is very important for just common picture. If we take any time variables, million, billion, doesn't matter, you will write huge system of equations, not observable. And you would like to say, I would like to write them in more or less compact form. Is it possible or not? So my claim is following. Since in these few particular cases, these equations have Lagrangian, this Lagrangian means that here is some hidden idea how to select appropriate choice for differential polynomials in terms of a0, a1, etc. In which, so this is appropriate coordinate nets. In these coordinates you can write corresponding Euler Lagrange equations. But if you go to higher time variables, it's local Lagrangians. This is impossible. But nevertheless, I believe that if it was possible for first integers, degrees, it should be possible for all others. Maybe if we, in appropriate way, will introduce such a new few variables, every time we will be able to write more or less compact forms for corresponding 3D systems. So again, I have very special, according to this procedure, rule how to write 3D systems, but they are not writable. Formulas grow rapidly, and it's impossible to write them in more or less simplest form. What to do? In my opinion, idea, we need to find appropriate coordinate net. If we do it due to this Lagrangian observation, local Lagrangian, then possibly we can extend this idea for higher time variables and then introducing so-called quasi-Lagrangian or maybe non-local Lagrangian densities. Maybe it will be hunch how to construct more and more complicated systems derived from appropriate Lux representation in 3D, maybe. So still this is open question. It's the best of my knowledge. Okay, so here I am no longer interested to speak about this observation. Now I am going to speak about 1D. 1D. So what means 1D? 1D means that I had, for instance, triple. Here is X, here I have T, here I have Y, 3D. When I'm speaking about, this construction, 3 equation instead of Lux pi, I have Lux triple. So I have separate evolution with respect to Y, separate evolution with respect to T. So this is one 2D system, the second 2D system. What means 1D? 1D, people usually say finite, dimensional, Hamiltonian. System, integrable, by Liouville theorem. So Liouville integrable. So I had 3D box, for instance, KP. Then I have a special machine how to split KP to two 2D commuting evolution systems. Next question, I would like to continue this reduction. What to do? Idea is following. Let us.
Yeah, to split the 2D to 1D.
Huh?
To split the 2D to 1D.
Yeah. We had a bridge from 3D to 2D, and now from 2D I would like to come to 1D. That 1D usually people call finite dimensional Hamiltonian systems integral by Liouville in Liouville sense.
Yeah, this separation of variables doesn't work again.
Yeah, works.
Yeah,
works.
it works again.
That I'm going to.
I see.
So we had phi t is L2 phi. Phi y is L3 phi. So what is it? This Lux representation for KP. Next, let us keep this equation. Lambda phi is L4 phi. And now I would like to reduce problem to 1D. What to do? Idea is following. Let's take, for instance, phi T5 is L5 phi. So I added this equation because I had infinitely many of them. So you see, in 3D case, I said we have dependence on x, t, and y. But of course, from the beginning, you remember I wrote t as a vector. T2, T3, T4, T5, infinitely many. So I wrote only these time variables which were important for me in this part of whiteboard. Now I say, oh, I remember that not only x, t, and y, not only z. So let's consider such a now dependence like phi depends on x, t, y, and parameter psi, for instance. And parameter, not parameter, time variable psi. So I write psi is identically t5 in my particular construction. Here. Now we say, let us consider an ansatz x, t, y, psi, and parameter lambda, you remember? Is psi of x, t, y, lambda, multiplying exponent mu psi. Precisely like here. Precisely. This means that once I substitute this ansatz to first equation, I come again. High t is L2 high y is L3 high. So I kept these two equations. Then I write lambda high is L4 high instead of this one. And now I remember that only this separation, combination of this, I'm speaking about this product, substitution here, lead me to the new equation which I can call mu high is L5 high. This is lux quadruple. This is 1D. 1D is hidden here. I'm going to speak about this. So again, I had 3D Kp determined by only these two equations. Then I said, okay, let's add one extra equation. Okay, we added. Then we come to 2D commuting systems. Then I say, okay, let's add fourth equation. When I add the fourth equation, here again, eigenvalue problem for operator A5. This operator should be compatible with this equation, and this one. In fact, known from Birchnell-Challenge construction, so result known, classical result known 100 years ago is following, that if you looking for common function high, which is a common solution of these two L5 two linear equations, they are compatible if and only if you can find some polynomial of lambda and mu. So this is some algebraic curve. Again, this is not my result, this is a result known in theory of computing differential operators, plenty papers, plenty books devoted to this question. I'm just talking about this inside of this picture, this polynomial P of lambda mu, this so-called Riemann surface. Inside of this equation is all information about corresponding so-called algebra geometrical solutions of Kp. So you have 3D box Kp, you selected according to this rule on infinitely many ways to 2D systems, and every such system according to this extra equation you can organize infinitely many polynomials of lambda and mu. So this way how to construct corresponding finite dimensional Hamiltonian systems integral in Liouville sense. So this is just such a scheme. How to derive exponents. So 1D means that here I had x, t, y. Now I had independently x and y evolution, x and t evolution. When I added fourth equation, this means I have evolution only with respect to x, with respect to y, and with respect to t. 3 commuting finite dimensional Hamiltonian systems integral in Liouville sense. So this is simplest picture which I wrote here, but simplest just ideologically, from the point of view that I explained in some algorithmic way what to do if you would like to derive corresponding equations. If you are interested in technological, not ideological, in technological direction, I said you, it takes time even if you use symbolic software. So it's much more complicated situation. I think so that theoretically this direction function psi again, this is scalar function. Such a program should be made maybe theoretically 40 years ago, theoretically, but still this is not yet solved problem due to just complexity of computations. It's interesting. Interesting. So in this way, this is again Gelfand decay reductions. I am speaking about 2D. This one. You can take L5, L7. This still Gelfand decay reduction. So this means that if you take pure differential polynomials according to this rule, when you check compatibility condition, equations which you shall be able to derive.
I think someone wants to ask a question.
Yeah, in this way you will go just to Gelfand decay reduction. So Gelfand decay reduction, I'm speaking about, this equation. You take any pair of this linear equation, and if you take pure differential operator, this definition of Gelfand decay reduction. This information about Gelfand decay reduction is hidden in this third equation. Pure differential operator due to this common formula. Yeah. If necessary, I can answer one question.
Yeah, I think I saw someone raise their hand, but yeah, anyway. Yeah, you can continue if the,
Okay.
Yeah.
So maybe in such case I can erase.
Yeah, you can erase.
Yeah.
I want to ask a question. You know, your 1 + 1 equation is nothing but hierarchical symmetries of PDB, isn't it? Yes, and the one-dimensional equations is a Novikov equation or whatever, stationary PDB equations which people use so everything was known kind of 50 years ago.
Sasha, you are right if we will fix time variables in appropriate way. What I'm talking about, lambda psi is L2 psi, this for KDV. Psi t is L k, doesn't matter, psi, and psi y, for instance, L m psi.
Сергей, это записывает на радиацию.
Yeah, so L2 means KDV. If you take L3, it will be Businesque. As example, if you change high and high differential polynomial, you will go beyond to KDV and Businesque hierarchy, so you will consider more and more complicated systems of equation. Of course, I can completely agree with you about Novikov equation for KDV hierarchy. Yes, that's right. Yeah. Okay, so let me just speak not about pure differential polynomials. It will be second sector. So first was Gelfand decay. Gelfand-Dicke means again psi t is L2 psi, psi y is L3 psi, and lambda psi is Lk psi. This is Gelfand-Dicke. Gelfand-Dicke reduction. So now I go beyond these Gelfand-Dicke reductions. So now I'm speaking about 2D reductions, still 2D, but beyond Gelfand-Dicke. Second, idea is following, very simple. At the best of my knowledge, this year, maybe I'm not precise, results obtained by Sasha Orlov, Boris Konopelchenko, and plenty mathematicians. I don't keep their family names, from China, from Japan, maybe also from Europe. So it was this result that I'm going to write was repeated independently by plenty of authors. So I just refer on Sasha Orlov, but of course I'm speaking about my private communication. But of course this paper, it's easy to find on the internet. Maybe it was Journal of Mathematical Physics. Anyway, what I'm going to tell you, you see what I said previously. I said we have still the differential period dx plus a naught dx minus 1, a1 dx minus 2, etc. We have lax pure differential operators organized in a way L in degree k and non-negative part. But now instead of this Lk, I will write, you see, maybe how to call them. Let us call me bk operators. So I write now Lk, Ik, plus p dx minus 1. You remember dx minus 1 q. So I had functions a0, a1, a2, etc. as functions of x and all higher time variables. Now p and q also the same. They are functions of x and all higher time variables t. So I added this extra block. Statement is that, you remember my picture here was psi tk is lk psi. It was such a picture from 3D to 2D. Now I write, let me write psi yk, new time variables. This is just my relabeling. Psi yk is bk psi. So I kept pure local differential part and I added this non-local block.
How do you apply it to the function psi, this non-local block?
X minus 1.
But what do you mean? Can you,
Integral,
what does it integral of in what sense?
like inverse operation to dx.
It does not exist. You need to integrate from
Yeah, but this question of just formal computer algebra. You say I determine this operation in this way. And of course, I agree with you that necessary to determine explicitly. I will speak about this.
Okay, but and what is q, by the way?
P and Q, some functions of as a0, a1, a2, etc. Some functions of x, t1, t2, t3, t4, t5.
So you first multiply by q, then apply dx to the power minus 1, right?
For instance,
if you act, yes.
L1, B1
Yes.
is dx plus p dx minus 1
Yes. So
V1 psi means psi x plus p dx minus 1 cube psi.
okay, so it
Yes, active on everything.
it remains to understand what this means. But okay,
Operate x on everything in right hand side. Okay, so again, what means integrability? Integrability means that, as usual, psi tk tm psi tm tk psi tk ym psi ym tk psi yk ym is psi ym yk for all integers, natural numbers. Should be correct, yeah? tk, yk, x, yeah, of course. So if you check compatibility condition, you'll come to such a little bit more complicated picture. And then you can ask me, if we have Gelfand decay, what are known examples? Okay, if you take k equal 2, I'm speaking about here, 2. This is KDV. If k equals 3, this is Businesque. What about these time variables, y? If I write, for instance, y1, this operator, it will be non-linear Schrödinger equation. Non-linear Schrödinger equation.
Do you always find something that is known before, an equation that we know to be integral? NLS, Businesque?
No,
Can you
I wrote here simplest known example. Yeah.
He has this construction gives an infinite collection of examples,
New.
and most of them are new.
Yeah. But scheme is so rigid. So in some sense, we can say nothing new because construction is simple. For instance, here you see I wrote p dx minus 1q. This picture, of course, can be extended. What means extended? Let me write. You see bk. I write in a appropriate form lk plus some m equal 1 up to m capital. M is arbitrary natural number. Pm dx minus 1 qm, you see. Instead of one term, I wrote here as many as you like non-local terms. What is important? So it was observation made not by me. That here we have only dx in minus 1 degree. No dx minus 2, no dx minus 3, etc. Only dx minus 1. But number of these blocks could be arbitrary. 1, 2, 3, 5, it doesn't matter. So beyond this construction, I am speaking of, for instance, b1 dx plus some pm dx minus 1 qm. What is it? This is vector, Monakov, NLS. So vector NLS version of Monakov is presented by this Lax representation. Arbitrary number of elements. So vector nonlinear Schrödinger equation can be written for letters P and letters Q. And usually people write them as a conjugate coordinates, complex conjugate. So for instance, PM are complex conjugate to QM. In this way, people write Monakov vector NLS. This is just a case. If you write B2, dx square plus u means A0, plus some pm dx minus 1 qm. This is so-called vector Yajima Oikawa system. Here. Known in some applications to some long short wave propagation. And you of course continue to extend dx cube, as I wrote for previous cases like Businesq. So any pure differential part plus this negative part. Its application give you appropriate representation. And last step that I would like to write here, last step, it's important of course. In this year, you can find this paper in internet. Igor Krichev introduced another reduction, 2D reduction. I will write it in very formal way and I will explain what is it. So you remember about, about this operator. So we would like to approximate this operator as, let's say, Q m plus n dx, Q m dx. So I have one pure differential operator. I have another pure differential operator. And the question is, what could be if I will divide one operator another one? Idea is following. It looks complicated, it looks like, but I can explain why it is not so complicated. You remember, L psi is lambda psi. You remember, for this operator I wrote several times. So let's replace L by this ratio. And let us multiply in appropriate way, I will explain what is it, on this denominator, left and right hand side. This means I come to Qm lambda psi is Qm plus n psi. So, what means Gelfand-Dickey reduction? Gelfand-Dickey means that here I write unity. If here I write some differential polynomial, pure differential operator, this extension of Gelfand-Dickey reduction. And my claim is following. If you are interested, you can look for in internet. I unfortunately forgot who was the second author. First one is Johann van der Leur. Maybe Sergei Gonin knows him.
Very well.
He wrote a paper about proof that reductions of Krichev, people call them rational reductions, are precisely the same as Orlov-Konopelchenko and some other people. So this is nothing but these reductions, nothing. So in another language, if you take higher order differential polynomial and if you write rule how in appropriate way correctly divide one differential operator to another one, their pure differential part is this one, and the rest of this procedure is given just by these blocks only. So indeed, equating this part to this part, you algorithmically can reconstruct all elements of this ratio in terms of P and Q, or vice versa. If you know these terms, you can know information about all blocks involved in this direction. So this is up to some integration complexities. This is just invertible procedure. So some people, due to Krichev way, prefer to use this language. Some people, as me, like this program, but doesn't matter because you see, here you have non-localities. Many people hate non-localities. Maybe Sergei.
I love them, but I need to know how to work with this term.
So instead then, you can use this blocks
Nice.
formula. Pure differential operator, pure differential operator. So again, this my finite words here. You have, for instance, psi t2, psi t is L2, psi y is L3, psi this is Kp, plus, as I wrote here, LQm psi is Qm psi, and all together, these equations go again to 2D systems. This way how to cut split KP to two commuting 2D systems. Without these terms, we had just multi-component systems commuting. If you add this block, this means that number of elements will increase according to this M capital. So this way, how to extend picture. Some people use these blocks. This name is known in literature. Plenty of people use it like self-consistent sources. At the best of my knowledge, this direction comes from Viktor Melnikov, who worked in Dubna. And now it's a very widely known mathematical direction in theory of integrable systems. Viktor Melnikov, I'm not sure, but mostly he was interested in direction to 2D. But now I'm speaking about 3D. So this means that, for instance, instead of L2 and L3, you can take B2 and B3 with M1 in M2. And again, it will be a 3D system. 3D system with non-local blocks. Why not? You can do it. Yeah, just I told you, problem is not from ideological point of view here, no problem. Problem in technological sense. Number of equations grows, and necessary to find such appropriate coordinate system where your system from compatibility condition could be written more or less in compact form. So here is the question: what is the hunch? How to find appropriate coordinates? My opinion is that appropriate coordinates come from Lagrangian structure, but this open question. So theoretically I can stop here. If my time in fact is over, or if I have some time I can speak about difference equations, but maybe we can just...
Well, in principle it's a bit over time, but we can ask, maybe people have questions.
Okay.
Sergey, can you switch on your microphone and ask if anyone has questions?
Pavlos, do you have any questions?
No, well, he didn't.
So there is only me and Pavlos.
No, on YouTube there are more people. Maybe someone wants to say.
Any questions to the speaker?
It's okay. No questions. Thanks.
Okay, yeah, thank you. Okay, in principle you can formally stop here and we can continue informally. Okay, thanks very much.
Thank you. Мы уже закончили, да?
Да,